Okay, I have started the recording. So again, welcome to all of you to this live stream talk. And it's going to be about variable stars in the open cluster NGC 6819. And as I said, this is really part of my research that I've been doing with collaborators in Europe who actually invited me to work with them on this project, and also with my student, Ann Hedlund, and my colleague, Jason Jackowitz at New Mexico State University in Las Cruces. So what is NGC 6819? Well, it is an open cluster, a cluster of stars in the constellation Cygnus, or Cygnus the Swan, as you may know it, pretty much straight up in the summer sky. This open cluster was discovered by Carolyn Herschel in 1784. And it is pretty far away, 7,500 light years away. The cluster age is 2.4 billion years, so it's half the age of our sun. Our sun is around 4.6 billion years old. And it's a faint cluster. The brightest stars are only 10th to 12th magnitude. To the naked eye, you can only see stars 6th magnitude. And then as you go up higher in magnitude, they're fainter and fainter. So this cluster, you could only see it really with a pair of binoculars. So that's why it took a while to discover it. And Carolyn and William, with their telescopes, were able to find these clusters and many other objects in our galaxy. So a little bit more about Carolyn Herschel. She is really an accomplished person. She lived between 1750 and 1848. She started out as a musician. She was an excellent singer and harpsichord player. But her brother William kind of left music and wanted to go into astronomy, and she didn't want to perform or sing without him. So she left music with him and sort of tagged along with him and became his assistant in all of his astronomy research. She was the first woman to receive a salary as a scientist, the first woman in England to hold a government position, the first woman to publish scientific findings in the Philosophical Transactions of the Royal Society, and she was the first woman awarded a gold medal of the Royal Astronomical Society in England in 1828. So, and there are many other really interesting facts about her on Wikipedia, so I encourage you to go read about her. She arranged 2,500 nebulae and star clusters into zones of similar distance from the celestial pole. And this list that she made became the prototype of the new general catalog, which is what we get our name NGC 6819 from, the new general catalog, is what that stands for. So why do we care about studying open clusters? Well, they give us some interesting constraints for stellar modeling. All the clusters should have formed together, all the cluster members, stars, should have formed together, and therefore should have a common age and initial element abundances. And knowing the cluster age and the element abundances gives us these constraints for stellar evolution. We know we have some starting points, at least, on how far we have to evolve the stars and compare with what we see in our stellar evolution. And also, I'll talk about this too, our stellar pulsation modeling. So I'll show you a few star clusters you might actually be familiar with, the Hyades and the Pleiades. The Pleiades is that cluster up in the upper right here. It is known also as the Seven Sisters. It's a lot of bright blue stars, very young stars in this cluster. I guess could take a poll at the end to see how many of you have actually seen the Pleiades, because you can't see them easily with the naked eye. And the other cluster that is down here, and it's kind of a V shape of stars. It's really the head of Taurus the Bull, and it's the cluster Hyades, and the star Aldebaran, which is a really bright star in the winter hexagon, is not actually part of that cluster, but it's in right near the V shape. So if you can find Aldebaran, you can find the rest of the Hyades star cluster. So there are a lot of other open clusters. And this picture, in fact, puts a lot of our open clusters on a diagram of absolute magnitude, or how bright the cluster members are absolutely, not taking into account their distance from us. And also, this is the color index, how blue versus visual magnitude differences are. So it's kind of a temperature measurement actually of these stars. So when stars are first born and they start burning hydrogen into helium in their cores, they line up on this diagram along this line here called the main sequence. And the sun in this picture is down here, and stars that are this is 10 billion. The sun hasn't finished burning its hydrogen into helium. It has a ways to go. But when it gets to about 10 billion years or so, it's going to start evolving off to the right in this diagram. Get my pointer to work, off to the right, and to become a red giant. So by plotting the stars, you can look at where the main sequence turnoff is. It's where the stars are starting to leave the main sequence in that cluster. And that tells you the age of the cluster. So this cluster M67 down here is actually around 5 billion years old. And you can go up here to Pleiades, it's actually like 1 billion years old. Stars are starting to evolve off. The Pleiades is only about 10 to the 8th, 100 million years old. And the Hyades, I think I read, is 600 million years old. And with that number has bounced around quite a bit during my career, 200 to 800 million years old. So these magnitude diagrams are really important to figure out what the age of the cluster is. We can overlay our stellar models and look at where they would finish their hydrogen burning and then tell how old the cluster is. So I think Chip Keller asked me this question the last time I gave the talk. He wanted to find out why the sun isn't in an open cluster. We have clusters that are the age of the sun in our galaxy. Where are the sun's siblings? Where are the stars that were born with the sun in a cluster? Well, we think the sun started in an open cluster, maybe of 1,000 stars, maybe 10,000 stars, just an estimate. But over time, the sun and other stars orbit around our Milky Way galaxy. And this picture is not actually the Milky Way galaxy, a real picture, because we are in the Milky Way galaxy. We can't actually fly above it and take a picture here above it and see the spiral arms like this and see the bar in the center. But it's kind of a composite of what we think the Milky Way galaxy looks like. And the sun is about 2/3 of the way out here in the Milky Way. And it's going around 20 times. It's gone around 20 times since the sun was formed 4.5 billion years ago. So the other stars in the cluster were also doing that, and they can get tugged at and pulled by nearby stars that are passing and get dragged away from the sun. And the ones that are closer in will go around faster than the stars that are further out. So eventually the cluster can get disrupted. And that's what we think happened to our home cluster. But have we been able to find any of these siblings? So people have been looking for them. They've been looking at nearby stars or stars that have similar element abundances and also are likely to be of the same age as our sun. And they sorted through thousands of these stars. And in 2014, this paper came out where they think they identified one solar sibling, HD 162826. So first of all, they've identified it based on metallicity or element abundances, and they think it has the same element abundances. And then they started doing modeling of our galaxy and how forces from gravity from nearby stars and the spiral arms with more dense material would have pulled stars around and tried to project back to figure out, could this star have been close to the sun? So they did that with a whole bunch of stars, but first I'll show you some detail about the solar sibling. It's actually magnitude 6.5, 6.6. So you could see it with a pair of binoculars, but you can't really see it naked eye. It's in the constellation Hercules, which is very near the star Vega, pretty much up in the summer and the early fall. And it's a little bit bigger than our sun, about 1.15 times the mass of the sun. It's about 110 light years away right now, so it's not that close anymore, but it has about the same age and chemical composition. And they actually have looked for planets around the star, and they haven't found any Jupiter-sized planets. They haven't ruled out Earth-sized planets yet around this star. So here's the little bit of a picture from that journal article trying to do these dynamical galactic orbit calculations to look for the candidates. And so they looked at distance, and 0 is the current time, and they looked back 4.5 billion years. And then this is velocity, and they're trying to look at stars that are matching the sun's velocity as they go around the galaxy. So they ruled out all these stars up here, these top 4. But here, if you look at this bottom star, you see that in the past, it's gotten within about 10 parsecs, or what is that, 30 light years or so of our sun. It stayed pretty close by our sun during the time going around the galaxy. And if you look at this, there are times when it almost matches the velocity. It gets faster sometimes and slower compared to our sun, but it almost matches. And this scale here, it varies for each of these. No, I guess it doesn't. It's always 10 to the 4, 10 to the 2. But this one is the one that they think is most likely to be a solar sibling, because these other ones are just staying too far away from our sun, both in distance and in velocity. So they might be close right now, like this one, but in the past, they project it was very far away. So this is our one candidate for a sister of the sun. All right, I'm going to go to another part of my talk and talk a little bit about the NASA Kepler spacecraft and that mission. It was launched in March of 2009, and the mission ended in 2018. And it used CCD photometry, or just basically CCD cameras arranged in a big array, and to look at the stars for a long time. They were looking at this right outside this spiral arm in the plane of our galaxy between the constellation Cygnus and the constellation Lyra. And their main mission was to look for Earth-like planets around other stars, and they found some. They mostly found bigger planets than the sun, than the Earth, but that was the start of looking for planets via transit. They were looking for eclipses. Like this picture here is just a picture showing a planet going in front of a star. If that does that, it blocks the light a little bit as it goes by, and then that tells us there's a planet there. So they found a lot of candidates. They confirmed many of them, thousands of them. But the second mission of this spacecraft was to survey and monitor the variability of stars themselves, the intrinsic light changes. Are they getting brighter and dimmer over time, and at what frequency, at what period are they doing that? So 100,000 stars were looked at, and this is a field called astroseismology, or using waves, seismic waves, to figure out what's going on in the inside of stars. And that's really what I do a lot of for my research. This picture is showing what that CCD array looked like after it was assembled on the ground before it got put into the spacecraft. So you see all these panels here were all arranged in this array. And then it was put on the top of this telescope, mounted up here. And this is the third stage. It's getting put on. And then it was launched in 2009. And it was launched in an interesting orbit. It wasn't launched around the Earth. It was launched around in the same orbit as the Earth, but trailing the Earth around the sun. So at the beginning, here it is, and here a year later, Kepler's getting farther and farther away from the Earth. But it's pretty much in the same orbit as the Earth around the sun. And I think in about 60 years, it'll actually come back around to get close to the Earth again. But we have turned it off, so we won't be communicating with it anymore. What was nice about this orbit is, though, because it didn't have the Earth blocking it, it could look at that field of view 24 hours, 7 days a week, continuously, without any obstruction. So that helped a lot with trying to detect planets going across other stars. This is its field of view for that first 4 years of the mission. And down here, you see this cluster fell on this particular spot in the CCD panels. NGC 6819 is down here. So that's the cluster that my colleagues wanted to look at and did a lot of research to try to understand the Kepler data from. There's one other cluster in this field, it's NGC 6811. And it's, I think, even older and fainter than NGC 6819. So the reason I'm pretty interested in NGC 6819 is that because of its age, at 2.5 billion years old, it has a lot of stars that are more massive than the sun that haven't yet evolved off the main sequence. So this is a picture of that color magnitude diagram like I showed you before, but for NGC 6819. And here you see the turnoff, and they matched it with an isochrone of models, so a set of stars of constant age. Around 2.4 matches really well, and that's how they get the age. And you see, though, there are a bunch of stars up here above the main sequence turnoff. These stars should have become red giants. They should have evolved off to the right and gone up here and become red giants, but they're still sitting there. So what's going on with those stars? Those are stars called blue stragglers, blue meaning because they're off into the left here, they're bluer and hotter than the rest of the stars, and straggler because they're straggling, they're not going over here like they should. So what formed these blue stragglers? Well, it's not known, but we think it could be mass transfer from a binary companion that we can't see, or even a binary merger sometime in the star's past that added fresh fuel and mixed the star up, and then it rejuvenated it. It put more hydrogen in the core so it could live longer. And what's really interesting about these is that some of these are pulsating variable stars. So we could use all of our tools of astroseismology or using waves, seismic waves, to understand the internal structure to try to figure out what's going on in these blue stragglers. So I'm really excited about that. So why do we care again about these pulsations or oscillations in stars? Well, they give us information about the sun, which is actually an oscillating variable star, and distant stars. Some of them pulsate in really big amplitude modes, and they can even tell us some things about the planets that we couldn't obtain if these stars were just constant, not pulsating. So they can tell us what's going on inside the star where we can't see. We can only really see the surface of the star. We can't see the inside and verify it's denser in the sun and denser inside, or doing anything inside unless we have some kind of other diagnostic. It'll tell us what the mass and the radius of the star is by using these different pulsation periods and their spacings. It can tell us how large a transiting planet is orbiting the star. So if we know the radius of the star and we know how long the orbit transit takes of the planet, we can use a scaling factor to determine how big the planet is. And it'll tell us what the age of the star is and what the age of the planet is. And that may be important if you want to think about colonizing the planet or knowing if there's life on that planet. You'd like to know how old the star is, how long it's been there, how long the planet has been there. So let's see if I can get this whole thing up. Almost. Okay, so this is an analogy to show you what pulsations would look like on other stars. This is a picture of a bell, and the sun and other stars pulsate kind of analogously to this bell. So when you ring this bell, the surface vibrates in and out, and it can vibrate in different overtones or harmonics all at the same time. So this particular picture is showing 3 different harmonics, one high frequency mode, one medium frequency mode, and one low frequency mode. And if you can isolate the frequencies by using this Dopplergram technique, you can see that certain patches of the star are vibrating in and out together or opposite, but then there's regions on the star that are a node line where it's not vibrating, where it's still. So you can fit different size patterns into this bell, and that's what determines its resonant frequencies. And so you've got, this mode here with the big patches, and then you have this mode with more smaller patches, and this mode with lots more small patches, so higher frequency. And I'm pointing to here the frequencies of the bell that they've analyzed with their acoustic techniques. So other stars do the same thing. I think I'll skip to this. No, I think I'll start here. So other stars have these same kind of patterns on the surface. And the stars I'm going to talk about that are these blue straggler stars or at the main sequence turnoff of NGC 6819 are Delta Scuti and Gamma Doradus variable stars. These are named after constellations in the southern hemisphere, so they don't sound Dorado and Scutus, the shield, and Doradus is a fish. So they're not constellations we are familiar with in the Northern Hemisphere. And these names are like the fourth brightest in that constellation, and Alpha Beta Gamma is the third brightest in that constellation. So they're named after these prototypes. These stars, like the sun, will pulsate in many modes simultaneously. So this is a diagram, this time with luminosity and temperature, where the hotter stars are on the left and the cooler stars are on the right. And this is the main sequence, again, where stars are burning hydrogen into helium in their cores. So the sun is a solar-like star, and it's down here. The Gamma Doradus stars are a little bit more massive up here, and then the Delta Scuti variables are here. So these Gamma Dor and Delta Scuti stars both have very different kinds of pulsation modes. The Delta Scuti stars are around twice the mass of the sun. They pulsate in acoustic modes, where pressure is the restoring force, so kind of like sound waves, just like that bell is vibrating. And because of their size, their periods and their frequencies are the periods are much longer, and their frequencies are much lower than a bell on the Earth. They're just huge, so they're going to have a very low pitch. You'd have to speed up the sound by 100,000 times to be able to hear what these stars would sound like if we could have sound waves coming out of them. The periods, I say, are around 2 hours of the different modes. And then we have the Gamma Doradus stars down here. These are a little bit less massive, about 1.5 times the mass of the sun, and they pulsate in gravity mode pulsations, where gravity is the restoring force. So you can kind of think of this like ripples or waves on the surface of the ocean, or if you jiggle some jello or wiggle a cup, you might see waves coming up and down, and those would be restored by gravity. Those are the gravity modes. And they have periods of around 1 to 3 days, so very long periods. It made them very hard to detect from Earth. So they were just discovered recently in the 90s for the first time, in the 1990s. So for distant stars, we can detect pulsation modes that are only have big patches on them, like those low frequency modes in that bell, where the variations don't average out over the disk. And that's because if these stars are vibrating in and out, you might have a hot region and a colder region, one that's coming out in velocity and one that's going in, and the yellow lines are node lines. And if these are big enough, if we look at the star just as a point source, the red and the blue won't average out from far away, so you'll actually get a signal where it'll get brighter and dimmer, or hotter and cooler. If we could measure that in spectral lines, we can do that over time. So we can get a light curve that shows that kind of mode. But if you get too many of these patches at a higher frequency mode here, like the one on the right, they'll average out over the disk. So the light curve signal will be very, very low amplitude. You could hardly see it, and you would need to have a very sensitive telescope and a very long time series observation to pull that out. Not that we can't with some of the, for L of 10 like this one, we think we should be able to pull some of them out if we have sensitive enough telescopes. So I'm going to show you kind of what I'm going to look for in the data here. And this is not some data from Kepler, but rather from the newer spacecraft TESS that is orbiting in a lunar resonance orbit around the Earth. So it's not quite as far away, and it's been up since 2018. It was launched in April, a little bit after Kepler, a little bit before Kepler mission ended. And this star is just one of the stars in the TESS input catalog. And you can see this light curve. This is basically the light, the brightness normalized, where 0 would be average brightness, but it gets brighter and brighter and dimmer, brighter, dimmer, brighter, dimmer. And all these dots are different points every, I think, 2 minutes they were taken for 27 days. And you can do a Fourier analysis or make a periodogram to pull out the frequencies, just like they did for that bell, and pulled out all those different frequencies in that graph at the bottom of that picture. So if you look at this one here, I see a whole bunch of modes right over here between 10 and 20 cycles per day. Well, that's basically 2 hours, whole lot of 2-hour modes. These are all the delta Scuti pulsation modes. And then I see a bunch of modes here with periods between 1 and 5 cycles per day, 1, 2, 3 cycles per day. And these are the gamma Doradus modes. So this star is actually pulsating both in pressure and gravity modes at the same time, which makes it really interesting. Plus it's a 4th magnitude star. So you can use it to, you could take lots of observations because it's really bright. You could do it with a small telescope even to find some of these things. So that is a really interesting star. And with tests, even with this short observation, we found more than 200 frequencies. If you just keep looking lower and lower amplitude, you can pull out 200 frequencies. So what do we do with these? Well, if you can find a simple enough pattern, which we haven't done for most delta Scuti stars, but these are some very young delta Scuti stars that were just formed. And in 2020, there was a Nature paper showing a bunch of these that were discovered mostly by tests, but also a few by Kepler. And you see that there's a lot of modes that have a very regular spacing. You can kind of find every certain amount of frequency, you see another mode. And by measuring that frequency spacing, we can figure out the density, average density of the stars. And also by looking at deviations in the spacing, you can find some more information about density gradients. So if we could find or decipher patterns like this in other delta Scuti stars, we would really be able to do a lot. And the same thing happens with gravity modes, but instead of looking at frequency spacings, we look at period spacings. And this period spacing is telling us, this is a particular Kepler star, that these this group pioneered this technique and found some of these for the first time. It's showing very regular period spacings, but it's also showing a change in period spacing with period. And by looking at this slope, they can figure out things about the internal rotation way deep in the star. Is it rotating faster than the surface or slower? Is there some kind of gradient? So it's really interesting diagnostic for the inside of the star. So now I'll go to my cluster, Kepler NGC 6819 data here for the cluster. So what happened was that they dedicated 200 by 200 pixels on that one CCD sector there. I forget their sectors and tests, some other name, module, CCD module it was called, that was centered on NGC 6819. So I'm not getting the whole cluster, but just the center of it. And each pixel is 4 arc seconds per pixel. Our telescopes can only resolve about 2 arc seconds. So these are actually pretty big pixels. And we took data with Kepler for 4 continuous years on this and just kept sending the data back to the Earth. The data was taken by collecting the light for 30 minutes and then storing the sums in the computer. And then every quarter, they would beam it all back to the Earth every 90 days or so. There were some gaps because a couple of the CCD modules failed during the course of the mission. So they had to kind of rotate the spacecraft to put it on another module to get data and spread it around. So everybody got their data that they wanted. This field is pretty crowded. As you see, there's some stars just overlapping in the pixels. So contamination is an issue with trying to understand the light curves. And we determined the cluster membership using some new data from the Gaia spacecraft. In fact, there was a data release just this Monday. The early data release is what we used, but the final data release 3 from this last set was done just on Monday of this week. And this data looked at parallaxes that would enable us to figure out how, if a star is moving back and forth, it appears to relative to background stars. You can use that information to figure out how far away the star is, and also proper motions. What direction are the stars going? And we think that the cluster members should all be going in basically the same direction, and they should basically be about the same distance away. So if we find that the star is too far or too close, or it's going that opposite direction, it's probably not a cluster member. So we had to go through all these stars and verify which ones were cluster members. So we picked out 5 stars for this paper we're writing. It's this first star I'm going to show you is Kepler Input Catalog 5024468. It's a magnitude 13 almost star, so you couldn't see it naked eye. It has to be in binoculars or telescope. It's in that blue straggler region of the diagram, so it should have become a red giant, but it hasn't. And it has an effective temperature about 7,000 degrees. So this is just a little snippet of the four-year light curve. So you see the brightness is going up and down over the average, and it's changing amplitude. You can see this envelope here. We have data points every 30 minutes on this picture. So this is just 5 days of data. So if you took a Fourier analysis of the whole 4 years of data, you can pull out a lot of frequencies. In fact, we pulled out 238 frequencies for this star. And they're all right around 12 cycles per day, right around 2 hours. So this makes it a delta Scuti variable, definitely. It actually was known as a delta Scuti variable before Kepler, but we couldn't find 230 frequencies with the ground-based data with just a short amount of data. And you can zoom in on this and see that there are some frequencies down here, low amplitude, that could be even gamma Doradus gravity mode frequencies, but we'd have to do some more work to rule out other possibilities. I'm not quite sure how we're going to do that yet. So one of the problems, as I said, with this field was contamination, and there actually was another star in exactly the same pixel, or very near it, maybe just the next pixel, Kepler Input Catalog 5024450. And this star is actually in an eclipsing binary. So its period, or its light curve looks like this. It's going up and down, but every 1.5 days or so, you see that one of the stars gets in front of the other, or you see an eclipse and the light curve drops out. So this signal, we had to actually subtract it out of the previous signal to get our frequencies. And if you tried to analyze this star, this is what would happen. You would see this comb-like structure here, which is from the binary periods, but you would see a whole bunch of 12 cycle per day frequencies in this light curve that are actually from that star that's so close to it, it's contaminating. So we have to be careful. We can't just say, oh, that's obviously a delta Scuti star in a binary. Well, really the delta Scuti star is next to it. It's not in the binary. All right, here's the second star. I'm going to show you about five stars total here. KIC 502408, a little bit fainter star, a little bit cooler. It's still in the blue straggler region. And here is its amplitude light curve here, amplitude per time. And this is a 50-day snippet. So it's a longer snippet because the periods of the modulation are quite a bit longer. So I put in a whole 50 days here. So you see it's going up and down with one data point every 30 minutes. And if you do the Fourier analysis, you see there's a whole lot of frequencies around half a cycle per day. So that's 2-day period, or 1 cycle per day, 1-day period. So this is definitely in the right range to be a gamma Doradus star. So when early Kepler data was taken, several groups were looking at this star, and they were interpreting this up and down as rotation and star spots, and even possibly differential rotation. So our sun has star spots and sunspots, as you know, and our sun rotates at the equator faster than it does at the pole. So our sunspots go around faster when they're near the equator than they do at the pole. And they were speculating that that could have been going on to cause a pattern like this in the star. So some of these frequencies might be rotation and star spots, but some of them also might be gamma Dor pulsations. And we also looked at very high frequency, and you see out here, we found one mode around 12 cycles per day, around that 2 hours. So maybe it has a delta Scuti mode as well, but with just one period, we can't really look for spacings, and we can't really confirm it's a delta Scuti star until we can, if we can find more. So, but definitely a gamma Dor star, I think. Okay, so this is the blue straggler region again for my third star. And this is 15th magnitude star, a little bit hotter. And this is a 20-day zoom in. Here's the light curve going up and down and up and down. And another Fourier analysis, we find a whole lot of modes, 1, 2, 3 cycles per day, right in the gamma Dor range. And we found 84 different modes in here with high enough signal to noise that we think they're real. This star was known in the past as a single line spectroscopic binary. So we think it has a binary companion going around it with about a 2-year period, but we can't see the binary companion. It's not eclipsing. It could be a small planet. It could be a really low mass star. So more work needs to be done to understand that. Maybe it's the star that dumped all its mass on this star and made it a blue straggler. And if we could find it, it might tell us what happened in the past with this star. So it'll be interesting. And then this is another 4-star, 15th magnitude. This is the hottest star I have. And usually the hotter stars, as you may have seen a correlation, hotter usually meant higher frequency, more likely to be delta Scuti star, lower temperature, more likely gamma Doradus star. This one has 124 frequencies. This is a 10-day zoom in, but you see it has this funny modulation, very low, long period modulation of all these up and down motions of the light curve, up and down, vibrations, we think, on the surface. And if I zoom in on that, you can see those more closely. You can see the high frequency part. So this is the low frequency modulation. Here's the 10 to 20 cycle per day modes that are the delta Scuti modes. And I plotted this out to 50 because you see that there's kind of a line here at 24.5 cycles per day. All these modes here are, we would have thought they were aliases, but there's some that have a higher amplitude than their reflection. This is because of the 30-minute cadence. We get this reflection in these aliases. But some of these in here are actually real frequencies. So this star actually has modes going up into the 30, 35 cycles per day region. So very high frequencies in this star. And then here's the final one. My colleagues gave this to me because they looked at the light curve and you see it's going up and down and up and down, just like a delta Scuti star would. Here's a 5-day zoom in on the light curve. But we took a Fourier analysis, and what we found were there were 2 really close frequencies that are just beating against each other constructively, destructively to form this light curve pattern. And then there's 2 here that are half that frequency, and then there's some aliases or harmonics of only these 2 modes. So this star is really only showing 2 frequencies and its harmonics. And we think it's some kind of a binary. It also has been observed in the X-ray, and it has chromospheric activity, creating basically X-ray flares and that kind of thing going on, at least on one of the stars, causing the X-ray. So whether these 2 stars are interacting or we're not sure, transferring mass, a lot more work needs to be done to figure that out. But on a HR diagram here, you can see the main sequence, and the star I'm talking about is labeled X9, the X-ray binary. So it's near the main sequence turnoff, but not quite there yet. Okay, so I'm going to conclude. Despite being born in the same cluster and having a similar location in the Hertzsprung-Russell diagram, that luminosity color diagram, each star has a unique light curve, and each of these stars have a different life story to tell. And the frequencies of these stars can help us figure out its life story. So of the 5 cluster members, we found 2 delta Scuti stars that are maybe also hybrid, 2 stars with low frequency variability that are probably gamma Dor stars, but we can't rule out rotation and spots or another kind of mode that's caused by the centrifugal force, and maybe Coriolis force. I could have this backwards. And 1 star that shows only 2 close frequencies in their harmonics. So we're going to probably publish what we have, or at least submit it to a journal. But in the future, we'd like to do the analysis on the frequency and period spacings and try to learn about the insides. We would like to model evolution in pulsations and take into account knowing the age and a common element abundance set can we figure out from that what is going on in these stars and why they are blue stragglers. And of course, if we can get more data, that will always be helpful, maybe to try to rule out pulsations from star spots, for example. So those are some things where there's infinite amount of work to do just on 5 stars. Okay, I'm going to stop sharing, see if anybody is still there, and see if anyone can hear me still. Heidi, would you mind maybe turning on your microphone and letting me know what's in the chat and asking some questions? If you have any questions, please put them in the chat.
Okay, sure. Can you see the chat?
I know I covered a lot. Whirlwind tour of everything, the space data, stellar evolution, stellar pulsation, a little bit about
Hi,
the
Joyce.
sun. Hi.
Joyce, hi, this is Nels Hoffman.
Yes.
One of your 5 stars had, I think it was the 3rd or the 4th, had this interesting, rather long period modulation of the higher frequency variations.
Yes.
Which you didn't explain that particular one. A later one, you said maybe it was a binary. What do you think about that one? Do you remember the one I mean?
Yes, I do know what you mean. And it's pretty low. Well, is it let me see if I can remember. I might have to bring up my own PowerPoint to check on it. I didn't zoom in on the period range, but it's very long. It's about 3-4 days. So that's kind of long to be a Gamma Dor star. I think it's a rotation period with some big spots.
Oh, okay.
So if there are big spots on the star, those look cooler, and when they rotate in and out of the field of view, they will make that modulation. But what I should do is look through the whole 4 years of data and see if that changes with time, or see if it's look at the properties of that period. How constant is it? Because I would think if it's a spot, it would go away after. It might go away after a year or 2, right? It can't. Star spots don't live forever. So yeah. But it looks like it's there most of the time. So if it isn't that, well, it could be a different star spot formed, and that could be also modulating it. And then you'd have to look at amplitude of that thing. Is it changing in amplitude with time? And it could also possibly be, as I was saying before, some kind of a pulsation, some kind of a Gamma Dor mode. So hard to rule these things out.
Yeah, okay, thank you.
Okay, so we have a question from Marilyn Doolin. How many variable stars are in NGC 6819?
Oh, good question. So very good question. I guess I am looking at 2 classes from my colleague Andre Barron. So I would need to ask him, because what he did is he wanted to find these subdwarf B type stars that are basically, they've lost their envelope and they're pulsating in some other kind of mode, gravity mode. So he was focusing on that kind of star, and I don't know how many he found, and I don't think he's published it yet. But he didn't want to do the Delta Scuti Gamma Dor because he said he didn't know anything about them. He knows more than he thinks, but he sent these to me. So I think there could be hundreds of pulsating stars in this cluster. And we haven't even talked about the red giant stars, right? There's red giants and those pulsate too. So yeah, there could be lots of different types of stars that pulsate. I'm just focusing on these 5 maybe 4 Gamma Dor Delta Scuti stars that happened to be in that little field of view right in the center of the cluster, that we could verify that we're cluster members, right? So there's a lot narrowing it down. So yeah,
Okay.
hundreds.
She asked a related question. How many stars have been analyzed? I guess in this cluster.
Yeah, good question. For pulsation, Not so sure. For binaries, they have done some papers on looking at binary stars in the cluster and using the binary orbit and properties of the stars to confirm the cluster age of the star and the distance of the cluster. So that's been done. And also, as you saw with that cluster HR diagram, they put all these stars on that in order to fit the age of the cluster. And then they've done a bunch of work with the red giant stars, but again, mostly to look at ages. So I can't tell you there's been a single star looked at for astroseismology yet. I haven't seen it. So they've looked at a lot of other things, a lot of other properties of the stars, but not the pulsations.
So Joyce, I guess I have a question for you. What's your opinion on blue stragglers? Do you think it's more possible that they collided, or if there's been a mass transfer, or both are probable?
I think both are probable. I think that there's probably a mixture of both types of formation scenarios. The mass transfer with some small companion that maybe we haven't detected, or the binary merger. I remember hearing a talk about a blue stragglers, and this person was claiming it was a mass transfer, but then they asked him, where's the companion? And he said you couldn't see it, couldn't find it. So that argues that, it was a merger, right? Unless you can find the companion. So another possibility that was very popular when I was in school was just that there was extra mixing in the stars, some kind of a instability in the core of the star that caused convection or caused mixing and pulled hydrogen from the envelope into the core, so kept it alive longer. But there hasn't been any credible mechanism, I guess, found for causing an episode like that. So that has fallen out of favor. But I think either are possible.
Okay, I appreciate that.
Joyce, I have another question. This cluster is half the age of the sun, as you said. So presumably then the cluster has taken about 10 orbital trips around the center of the galaxy in its lifetime. Yeah. And yet this cluster is still very condensed. All the stars are still clustered together pretty well. So what's the difference? Is it just that it's more gravitationally bound than the sun's birth cluster was?
Possibly. It may have started out with more stars too. And a lot of them have evaporated away or gone away, been ripped away, but this is the part that's left that's more gravitationally bound. It's a good question, and I'm not a galactic dynamics expert, so I can't say, its position in the 7,500 light years away. I don't know how it's positioned relative to some dense feature in the galaxy, like a spiral arm or something. So
there could be places in the galaxy where a cluster is more likely to be disrupted than other places.
Yes, yeah. That's what I think. So I think the sun in that picture we saw, they were pointing to a place kind of close to a spiral arm. So it's maybe the sun's cluster was close to more dense stuff and it got ripped apart, whereas this one is not. I should find out exactly where it's situated in the galaxy and get back to you. It's a good question. Yeah.
Okay, thank you.
Maybe it's far, maybe it's off the galactic plane enough that it avoids some of the, the shredding. Yeah.
Yeah.
Why don't you check that out? I'll ask Andre, he'll know, my co-author.
Okay.
Those are good insights. I mean, it does seem possible that if you had a larger cluster that was more gravitationally bound, there would be still some members held together, to me.
Mm-hmm.
Yeah. So there's a couple of comments from Gary V. You are a one-woman show, you go, girl. I agree. Awesome job. And he also wants to know how he can contact you via email, if that's okay to
Yeah,
ask?
that's fine. I'll type my email in the chat. It's very easy. It's joy@lano.gov. And it's really a two-woman show because Heidi has been moderating and keeping me out of trouble here. So I hope you were able to hear and see okay. I don't know from my
It looked
side.
great,
Okay.
really.
Okay. All right, well, I will sign off then. Thank you again for joining us, and we will see you hopefully at future Zoom talks or in person.